So we're going to talk today about kind of two concepts, and a lot of what this has to do with is all chapter 1 stuff. So remember in chapter 1 when we talked about continuity?
Yes.
Okay, and we had that slang definition of continuity was we could trace it without picking our pencil up off the paper, but what were the 3 things we needed to prove in order to show something was continuous? So it can't have a hole or a vertical asymptote, and that was all great, but that wasn't part of our proof. I think you're on to it. First, what?
Yeah, the two different limits had to be equal.
Yeah, so just the limit, just to kind of wrap all that up, the limit has to exist. Okay, which means if you're dealing with a piecewise function, the left-sided limit has to equal the right-sided limit. Okay, what was also in addition to the limit? The point has to exist. The left side and right side equaling each other is all incorporated up with that number 1. The second one was the point had to exist, and then the third one was that they had to equal each other. And it's been a while since we've done this, so hopefully it'll come back quickly, but this is why it's just good to kind of go over this stuff and not leave it alone for too long. So that's how you prove if something is continuous. So what we're going to do today is prove whether something is differentiable. Well, here's the deal. You have to prove continuity first. If something is not continuous, it cannot be differentiable. All right, and then differentiability, it has its own step. Okay, so looking at number 1 here, this is not a piecewise function. I could probably draw it as one, or write it as one. What I'm going to do instead is actually draw the function. It's an absolute value graph shifted to the right one. And so that's not my proof, but I'm going to use that to help guide me in the proof. So number 1, does the limit as x approaches 1 exist? Or what is it? 0. The limit is the y value. As x gets really close to 1, what is the y value? And so that thing exists. You don't have to write the phrase exists, but I'm going to write it there. Okay, what was the second thing we had to show? F of 1 has to exist. And what is f of 1? Is there an actual point there? There is, and that's also 0. And again, you don't have to write this word exists. I'm writing it just to really show like what we've done. And then the third thing was you had to show that they were equal. So this is how you prove that this thing is continuous. What you found in part 1 is equal to what you found in part 2. And the notation was, I think, really what got people like, once they understood it, the notation still kind of caused some problems. That's going to get easier with practice. So once you've done those 3 things, then we can say, therefore, f of x is continuous. And you need to say at, I'm going to write this on the next line, actually, at x equals 1. That's all we proved. We didn't prove it's continuous everywhere, just at x equals 1. And that's all old stuff. Okay, we hadn't done it in a while. We needed to review it, but it's all old stuff. Okay, the new stuff has to do with differentiability. So we first proved continuity. Now we're going to prove differentiability. By the way, if this function is not continuous, you don't even have to do anything else. If it's not continuous, we have that it's not differentiable. Okay, so what we need to do is, if we can find the derivative, we need to find it. Okay, do we know how to take the derivative of an absolute value? Do we have a rule? No. We could do it by definition of the derivative. We could write this as a piecewise and do it that way. For this particular problem, we don't really have to do it at all. But when we get into the other ones, we're going to actually find the derivative. But what I am going to do is analyze the limit as x approaches 1 from the left of f prime. Hopefully you're writing a little bit smaller than me. So graphically, what is f prime on this graph? the slope. Okay, over here in red, I was talking about just regular old limits, and that had to do with y values. Over here in blue, I'm talking about differentiability, the derivative, and I'm talking about the slope. So what is the slope on this left side of the graph? -1. Okay, and what I really want is that the slope on the right side to be also -1. That's not going to happen. And what is it? +1. Now, because these are not the same, this thing is not differentiable. If they were the same, then I would say that the derivative at 1 is 1, or -1, or whatever the number ended up being. So this thing, we can say, therefore, f of x is not differentiable at x equals 1. Okay, before I move on to the next problem, do you guys understand why I had to say f of x here? Some people think I should put f prime. Yeah, go back to the original function. By analyzing f prime, I'm saying something about the original function. If I said f prime is differentiable or not, that would be like the derivative of the derivative, second derivative, which we're not dealing with here. Okay, so that is how you do one type of problem, okay? Now, all the rest of these are piecewise functions. So we're going to approach them a little bit differently, okay? We're still going to go through the same steps, but improving continuity and doing the derivative, we get to do something else. And I'm going to definitely run out of space because I'm writing too big, or I should have zoomed in or something. Anyway, so what is the limit as x approaches 2? And I do, because there's a left and a right-sided part of this, I need to go ahead and do that up here. I didn't have to on number 1. I need to do that here. So I need to put a negative, and I need to show which piece I'm actually plugging it into. So what is the limit as x approaches 2 from the left? What happens when you plug 2 in? 2 squared plus 1, that's 5. What about the right-sided limit? That also equals 5. I'm going to write that up there just so I have some more space. So because the left side and right-sided limits are the same, I can go forward. What if they had been different? You'd stop right there. You'd say limit doesn't exist, not continuous, not differentiable, move on to the next problem. But because these two are the same, I need to go ahead and write down what this means. It means that the limit, not the left side or right sided, but the limit equals 5, which exists. And then go to part 2, which is the point. Now the point, f of 2, is going to occur at whichever piece has the or equal to. Okay, so we already have plugged this in. You can show it again. You can go ahead and write equals 5. Most of the time on these piecewise functions, if number 1 is true, then probably 2 and 3 are true. And then 3 would be to show that what we found in number 1 equals what we found in number 2. And all of this to show that f of x is continuous at x equals 2. And again, I hope you're writing just a tad bit smaller than I am. Because what I'm going to do is I'm going to continue down here, but then I'm going to have to erase it. Okay? If not, you just draw arrows or whatever. I'm sorry. Okay, so for right now, I'm going to do this. Don't do that on your own paper. We are going to go back and do number 4. I'm going to have to erase it. Okay? Or you can write it and then erase it. These are your notes. You do whatever you want to do, I guess. Okay, so that was all great. But now I need to do the derivative piece. So taking a derivative of a piecewise function, it's actually exactly what you think it would be. You take the derivative of the first piece. That would be 2x. And you write the exact same x less than or equal to 2. So what would the derivative of the next piece be? 4. So now you know how to take derivative of a piecewise function. Just take derivative of each piece. And we're going to analyze this. We're going to find the derivative from the left and from the right. We don't have to write out all the steps quite like this. We still need to use good notation, though. We need to say the limit as x approaches 2 from the left. And we're going to go of 2x. And what would that equal? 4. Plug in 2. 2 times 2 is 4. And then we need to find the limit as x approaches 2 from the right. And we'd plug that into the second piece, which is 4. And since there's nowhere for x to actually be plugged into, that second derivative would always be 4. And what these things are telling us is that f prime of 2 equals 4. It's telling us what the derivative is. And so we can say, this is all working out, so we can say, therefore, f of x is differentiable at x equals 2. If these had not both been 4, what do you think my therefore would be? Not continuous. Okay, what this means is that I have two things, and I'm not really going to draw a very good picture of this. I'll show you a picture of what it looks like. It's not the picture of this one. But imagine you have a parabola, and you stop the parabola, okay? And you draw a line. Now the line has the same slope. That's what's happening here. Okay, what would be bad, we're going to see this in a minute, is if you had something like this. That's not differentiable. But what's happening in this example too is that even though I have two different parent functions, they're meeting, and right where they meet, the slope is the same at that point. Okay, so I'm going to erase all of this now at the bottom. We're going to do two more examples. So really the hardest examples, or maybe not the hardest ones, but the ones you have to do the most work for is where everything works out. It's actually nicer when it doesn't work, because then you get to quit and say, not differentiable. All right, so number 3. I want you guys to go ahead and do the 1, 2, 3 part on your own on this one. And I'm going to... Okay, so how are we feeling about this? The continuity piece. So this should just be getting easier. I mean, you kind of had to do a couple to kind of get refreshed on it, but hopefully it's making more sense than, you know, the first day that we did it. Okay, now we need to do the derivative. So we got to take the derivative if we can, which we can on this, because now you know how to take the derivative of a piecewise function. The whole x less than 1, x greater than or equal to 1, that all just stays the same. You don't take derivative of that part. We do need to figure out what is the slope or the derivative as x approaches 1 from the left. So I got 1 for that. What about the other side? I got 2. So this is one of those situations, and I'm not really graphing this graph, but it's a situation where you have a parabola and a line meeting. They're continuous. They are meeting, but they're not meeting at the same slope. Sorry, I just had to exit that out. They're not meeting at the same slope, so that's not differentiable, and we call that a cusp. You've heard that word before. So we do need to say, therefore, f of x is not differentiable at x equals 1. That's all we're analyzing here. Okay, number 4 is the perfect example of why you have to do continuity first. If we try to do the derivative part of number 4 first, what would the derivative be of the two pieces? The same, and you'd think it was differentiable. Okay, but we're going to find out here in just a minute that this thing is not continuous. So we find the left-sided limit. That ends up being 4. We find the right-sided limit. And that ends up being -1. So the limit as x approaches 1 does not exist. We should probably write that. Therefore, f of x is not continuous at x equals 1, which means it's not differentiable. So it's kind of nice when this happens early on. It really saves you the work. What this looks like graphically is that you have, again, I'm not really graphing this graph, but something where we can see it more clearly, it'd be like this. Where maybe the slope was the same. This is not a picture of what I just did. But you can see here that there's two parabolas here. They have the same slope, but they're not meeting, so it doesn't matter. Okay, let's look at the next page. So that was a little review of continuity and limits. Let's talk a little bit more about limits here. This right here is L'Hopital's rule. It's French. Sometimes there's an S there and it looks like La Hospitals. But either way, it's L'Hopital's rule. We are going to, when we write this, just write LHR. And so how do we evaluate limits? I mean, we just did this. So what did we do to evaluate those limits? Plug it in. 2 squared minus 4 over 2 minus 2. And in this case, we don't get a number. We get 4 minus 4 over 2 minus 2, or 0 over 0. I've talked about this before, but I think today you'll have a better understanding. 0 over 0 is not 1. It's not 0. It's not infinity. It's really not even undefined the same way a number over 0 is undefined. Okay? That is undefined. You can't do anything with that. But 0 over 0 and infinity over infinity are something we call indeterminate form, which means that we just don't know. The answer could be 0, it could be 1, it could be another number, it could be undefined, it could be infinity, but we don't know yet. Indeterminate form. There are other examples of indeterminate form, but these are the only ones that we're going to see. So in the case where you have indeterminate form, what you can do is you can apply L'Hopital's rule. You need to make sure, though, that you're getting 0 over 0 before you apply it. This is the same example, so I'm not going to go through the arithmetic, but you get 0 over 0. And so what L'Hopital's rule says is that you can take the same limit and just take the derivative of the top piece and the bottom piece. This is not quotient rule. We're not taking derivative of the whole thing. And now plug in again. So we go 2 times 2, and that would equal 4.
That's also what you get when you do more.
Yep, so I'm going to go back to the top one and talk about that. So do y'all remember do more? So before today, what you did on this type of problem is you did algebra. You factored, and we're going to get the same answer. And then you plugged in 2. So this is kind of like a different version of the do more. Okay, next time you see a problem like this, it really does not matter to me which way you use it. You can do it how we did it before. You can use L'Hopital's rule. Let me show you a problem that we could not have done before today. Okay, example 1. You plug in 0 in for x, you get sine of 0 over 0. Sine of 0 is 0. Okay, there's no way we can factor sine x over x. This is something that some teachers have their students memorize. I don't really worry too much about it because I know that it's going to get covered here when we do L'Hopital's rule. So we get 0 over 0, apply L'Hopital's rule, which means we are just going to take the derivative of the top and the derivative of the bottom. We're not taking derivative of the whole thing like quotient rule. This is just a rule, like a shortcut. And once you do that, you should be able to plug 0 back in and actually get an answer. Cosine of 0, anybody?
1.
So 1 divided by 1, that's your answer. You did see a problem like this at the beginning of the year, but it was on the when we did the table on the calculator. So this is how you would do a problem like this without the calculator. And now you know. Okay, let's look at problem 2. Always plug the number in. You have to confirm that you're going to get 0 over 0 before you decide, hey, let's try L'Hopital's rule. We did see problems like this at the beginning of the year. Does anybody remember how we got rid of that square root? You multiplied by the conjugate. And you may or may not remember this, but it kind of got messy. Okay, you can totally get out of that by doing L'Hopital's rule. So we're going to rewrite the limit as x approaches 1. We're going to take the derivative of the top and then the derivative of the bottom. What's the derivative of the top? 1/2 x to the negative 1/2. Rewrite that as x to the 1/2 if you needed to. Derivative of the bottom is 1. And now we're going to plug 1 in because that's what I'm doing my limit as. 1/2. 1 to the negative 1/2. Don't think too hard about this. 1 to anything is 1. So your answer is 1/2. This is so much easier than doing this algebraically. So much easier. And if you're already thinking, why didn't I show you this? Well, you didn't know how to do derivatives back then. That was something we hadn't even talked about yet, really. Okay, look at 3 and 4 now. 3 and 4, see that limit as x approaches infinity? We've actually already done those. Do y'all remember how we did those? That was when we did one-sided limits. But we did, so when x is getting really, really big, we're talking about the really extreme sides of the graph. These are horizontal asymptote rules. Low over high, 0 equals y. Degrees are the same, play the coefficient game. So I'm going to work these out, L'Hopital's rule in a minute, but does anybody know the answer to number 3? 0 is correct. What about number 4? 1/3. So if you already knew that, then really that's how you should do this problem because that's working well for you, okay? But let me show you just what happens anyway. So we plug in infinity, right? 3 times infinity is infinity. Infinity squared plus 6, that's also infinity. This was one of the indeterminate forms. It could be 0, it could be 1, it could be another number, it could be infinity, whatever. So we're going to apply L'Hopital's rule. So we're going to take the limit as x approaches infinity still. But this time when I write it, I'm going to take derivative of the top and derivative of the bottom. And I'm going to plug infinity in again. And this time I have 3 over infinity. What is 3 divided by a really big number? It's a really small number, and when we're talking limits, we're talking 0.
What if the infinity was on top?
If the infinity, what do you think? If the infinity was on top, if we had a problem where we had infinity over 3, what would a really big number, what would happen to you if you had a really big number and you divided by 3? Wouldn't you still have a really big number?
Yes.
So that would be infinity.
So the answer's already been 0 or infinity.
Well, or in number 4, we have a different scenario.
Oh, yeah.
So we get infinity over infinity. We do L'Hopital's rule. So we go limit as x approaches infinity. And then we go 2x over 6x minus 8. Hopefully this is showing you like why that stuff doesn't matter in these problems. And we plug in infinity and I get infinity over infinity again, which really just means, hey, do L'Hopital's rule again. Sometimes you got to repeat the process. And now I just get 2, 6. There's not even an x to plug in. So my answer is 2 6 or 1/3. It's the same thing you get. I'm not saying you have to use L'Hopital's rule on these problems. It's just a strategy you're just going to put in your toolbox and use when you need it.
So if you know that it's 1/3, you have to still do all that.
No. If you can look at this and know that it's 1/3, you're good to go. This type of question on the AP exam is going to either be multiple choice, which means you're not getting graded for your work, or if it was free response, they're not going to require to see your work because this is something you can do in your head. The reason we need L'Hopital's rule, though, is for the problems we can't do any other way. And you're going to see a little bit of that on your homework, like some AP test questions. So let's look at number 5. Does this look familiar at all? This is totally definition of the derivative, just like what you've had on your after parties. So can anybody tell me what they know, like, forget about L'Hopital's rule. Like, how would you have done this yesterday?
Take the derivative of the f of x.
Yep, you'd look right here and you'd say, okay, I see sine of pi after that minus. So that means that my function is sine x, which means I take the derivative and then I plug in pi. Anybody know what cosine of pi is? -1. So that's my answer. I'm not pretending like we can't do this another way, but let me show you what happens here. If you were to plug a 0 in for h here and here, you do get 0 over 0. Do you guys see that? You get sine of pi minus sine of pi over 0. Okay, so we can apply L'Hopital's rule here. We get limit as h approaches 0. We take derivative. So derivative of sine of pi plus h. That would be cosine of pi plus h times the derivative of pi plus h, which would be 1, minus sine of pi is a number, right? What's the derivative of any number? 0. And then h, the derivative of that would be 1. And now we take the limit. See what happens when we plug 0 in for h? We get cosine pi, the same way that we did before. I'm just kind of showing you that even though this is different, you're still getting the same answer. It's still actually a pretty similar process. Okay, number 6. This is actually called the alternative definition of derivative. It's not something that I really teach y'all as something to memorize because you can use L'Hopital's rule. I find that when I go over this and when there's 2 of these, it gets confusing. So we're just I want you to know that this is something you may see again, but we're going to just use L'Hopital's rule here. And there's too much going on, so I'm going to box that off. So what would happen if I plugged 2 in and just try to solve the limit that way? Yeah, I get f of 2 minus f of 2 over 2 minus 2, 0 over 0. And so now I apply L'Hopital's rule. So limit as x approaches 2, that part stays the same. What would be the derivative of the top? Well, the derivative of f of x would just be f prime x. I don't really know what that is. But what about f of 2? Why would that thing's derivative be 0?
Because it would be a number eventually.
It would be a number. F of 2 is a number. And so derivative of f of 2 is always going to be 0. Derivative of the denominator is 1. Plug in your 2. You get f prime of 2. So this is just another way of explaining derivative. Okay, it's something I could have had you guys memorize, and okay, that's great. If you're like really interested, I can show you this someday. But it's pretty easy to do with L'Hopital's rule, and you don't have to memorize a new formula. Okay, some people by the end of this, they love L'Hopital's rule so much they want to use it on every single problem they ever see, and that's a problem because if you tried it on this next one, you would get it wrong. Okay, do not over apply the rule. Always start by plugging in the number that you're taking the limit towards. Okay, here we just get -6. That is your answer. Move on with your life. Okay, you don't want to use L'Hopital's rule here. It's not even that you don't have to do the work, it's that it's going to give you the wrong answer. You only use L'Hopital's rule when you have 0 over 0 or infinity over infinity. There are some other cases, but these are the only ones we're going to do.